You know, for literally decades, we've been hearing the exact same story. Quantum computing is the technology of tomorrow. It's always 10 years away, always completely theoretical. Well, looking at the latest data, we can officially say that tomorrow is today. We are tracking some massive, industry-shaking shockwaves hitting the tech world across 2025 and 2026, as quantum systems are finally outsmarting classical supercomputers. The so-called quantum winter is completely over, and we have officially entered the quantum sprint. To really wrap your head around the sheer scale of the breakthroughs we're talking about, just listen to this quote from Dr. Anthony Ransford, who's a lead architect over at Quantinuum. He says you would literally need to harvest every star in the universe to power a classical machine capable of doing these exact same calculations. And he's not just hyping up their new hardware for marketing. Mathematically speaking, that is a literal fact. The computational power we are deploying right now physically cannot be matched by any traditional supercomputer ever.
And if you want a really concrete example of what that looks like in the real world, check out this number. 5 minutes. That is it. That's exactly how long it took Google's new Willow chip to complete a random circuit sampling benchmark, which is essentially just a staggeringly complex mathematical maze. Now, if you asked Frontier, which is the absolute fastest classical supercomputer on Earth right now, to run that exact same calculation, it would take an estimated 10 septillion years. Think about that. The gap isn't just big, it's 24 orders of magnitude wide.
So here's our roadmap for today's explainer. First, the quantum spring arrives. 2, hardware breakthroughs redefining compute. 3, the hybrid computing bridge. 4, the commercial tipping point. And finally, 5, real-world impact and risks.
Starting with Section 1, the quantum spring arrives. From theoretical physics to verifiable reality.
So, what's the big deal with quantum advantage? Well, for years, skeptics argued that quantum machines were a dead end because they'd become way too noisy and error-prone as you made them bigger. But Google's 105-qubit Willow chip just totally proved them wrong. By crossing this critical error correction threshold, Google proved that, actually, as you scale these systems up, the error rates can decrease. And, to silence the critics who said, hey, these calculations are too complex to even verify, Google introduced a deterministic signal called quantum echoes. It's basically a digital fingerprint that proves, without a doubt, the machine got the math right. So yeah, quantum advantage is now a verifiable reality.
Moving into Section 2, hardware breakthroughs redefining compute, the trio of quantum marvels.
Right now, we are in the middle of a fiercely competitive hardware race. You've got Google's Willow relying on superconducting qubits to hit an insane 99.97% single qubit fidelity, meaning its baseline accuracy is just off the charts. Then, taking a completely different route, you have Quantitunia's Helios system. They're trapping individual barium ions with electromagnetic fields, getting a staggering 99.1% 2-qubit fidelity. And then you absolutely have to look at Rigetti's Cepheus system. They've built this incredibly smart modular rig using 12 interconnected 9-qubit chiplets, and it runs at lightning-fast 60 nanosecond gate speeds. It's honestly like comparing a jet engine, an electric motor, and a rocket. They're all totally different, but they're all built to solve the same immense mathematical problems.
But it's not just about raw speed, right? It's about endurance, and this is where a totally separate breakthrough from Harvard and MIT flips the script. Historically, quantum computers ran in pulsed modes. You'd run a calculation until the atoms literally vanished or lost their quantum state, and then, bam, you'd have to stop and reset the whole thing. Well, Harvard and MIT just demonstrated a continuous 3,000-qubit system. They built these wild optical conveyor belts using lasers that can reload 300,000 fresh rubidium atoms per second right in the middle of a computation. It's exactly like replacing a burnt-out light bulb in your living room without ever turning off the main power. The machine can basically run indefinitely now.
But look, having thousands of raw physical qubits kind of doesn't mean much if they're super unstable. To make these machines truly useful for enterprise stuff, we desperately need stable, error-corrected, logical qubits. And boom, Quantitunium just dropped an absolute bombshell here. Using their proprietary Iceberg code, they took 98 physical qubits and successfully extracted 94 logical qubits from them. I mean, just let that sink in for a second. That is an encoding rate that the entire industry thought was physically impossible just a couple of years ago. It means we don't need millions of physical qubits to start doing highly complex fault-tolerant work today.
Section 3, the hybrid computing bridge, uniting quantum and classical forces.
Now, we aren't just throwing our classical computers in the trash. IBM put out a blueprint for quantum-centric supercomputing, and it shows the future is really about these systems working perfectly together. It works in 3 distinct steps.
First, your classical supercomputers and beefy GPUs handle all the bulk logic and standard data processing. Second, orchestration software, stuff like NVIDIA's CUDA-Q platform, acts like a traffic cop, routing the workflow. Third, when the system hits a staggering bottleneck, like simulating a really complex molecule, it routes that specific subproblem straight to the Quantum Processing Unit, or QPU. It's the ultimate tag team approach.
Next up, Section 4. The commercial tipping point. Capital meets computation.
With this hybrid hardware bridge fully online, this technology has officially left the academic labs, and the money proves it. According to the McKinsey Quantum Technology Monitor, startup investments absolutely skyrocketed in 2025. They jumped 6.3 times higher than the previous year, hitting a massive $12.6 billion globally. That is what a commercial tipping point looks like, folks. Private capital is just flooding the zone because for the first time, the path to a real-world return on investment is crystal clear.
And what's really crucial to note is how concentrated that funding is. The broader quantum industry obviously includes things like sensors and communication networks, but a massive 90% of that $12.6 billion poured exclusively into quantum computing startups. Investors are placing massive bets on the exact hardware, software, and hybrid orchestration layers we've been talking about.
And that money is already doing real work. Over 300 global organizations are actively running hybrid use cases today. You've got JPMorgan Chase using quantum algorithms for highly complex portfolio optimization. Airbus is using it to entangle these massive logistics and route constraints. And over in life sciences, the Cleveland Clinic successfully simulated an incredibly complex 303-atom protein structure. By running molecular simulations like this on quantum-centric supercomputers, pharma companies are basically poised to shave years and billions of dollars off the drug discovery process.
Which brings us to our final section. Section 5, Real-World Impact and Risks. The countdown to Q-Day.
Okay, we really need to talk about the flip side of all this power. It brings a massive, urgent, and quite frankly, civilization-level cybersecurity threat. The clock is absolutely ticking here. Google has publicly stated they're targeting a 1 million qubit system by the early 2030s. That timeline accelerates us incredibly fast towards something called Q-Day. Q-Day is that terrifying exact moment when traditional public key encryption, like RSA 2048, which secures literally the entire global internet, is instantly broken by a quantum computer. And because of this, bad actors are actively executing a strategy right now called Harvest Now, Decrypt Later. They are stealing encrypted data today, hoarding it, and just waiting for machines like Willow to scale up so they can easily unlock it tomorrow.
Because of this looming threat, transitioning to government-standardized post-quantum cryptography, or PQC, is simply not optional anymore. It is an immediate mandate for every major enterprise. Financial institutions, healthcare orgs, governments, they are all under immense pressure right this second to upgrade their security protocols. Listen, if your organization holds on to long-lived sensitive data, you absolutely cannot afford to wait until Q-Day actually gets here, because by then, the data you're trying to protect will already be compromised.
So, bringing it all together, we've seen how the impossible is rapidly becoming totally routine. Hardware limits are being completely shattered, hybrid systems are online, billions are flowing into the ecosystem, and the cybersecurity clock is ticking louder than it ever has before. So I want to leave you with this final thought. The quantum spring has undeniably arrived. The technology is here, but is your organization truly prepared for the shockwaves it's bringing?